read told us that if we have 0 times infinity or negative infinity, we don't know what that's going to be. Okay, sometimes that answer turns out to be 0, sometimes it turns out to be infinity, sometimes it turns out to be a number in between. So what we have to do is rewrite our product as a quotient so that we can apply L'Hopital's rule. So let's look at this example. The limit as x approaches 0 from the right of x natural log of x. All right, so currently what we have is 0 times the natural log graph. As you're approaching 0 from the right, it's going to negative infinity. So we don't know what that is. What we're going to do, and this is on your notes handout from yesterday. Right, so we want to rewrite this as a fraction. Now I don't really want to move my natural log down because I would have to do 1 over the natural log of x. But what I'm going to do is take this x to the denominator by dividing by the reciprocal. I'm going to make it a 1 over x. Okay, mathematically this is the same. To divide by a fraction, you flip and multiply. So this is equivalent to what we started with. Does everyone see that? So to move it down to the bottom, I just had to make it the reciprocal. Now, the top, as I'm approaching 0 from the right, the natural log of x is going to negative infinity. On the bottom, 1 over a smaller and smaller and smaller number is going to infinity. So now we have infinity over infinity, which means we can do L'Hopital's. Okay, L'Hopital's rule says to evaluate this limit, we can do the derivative of the top and bottom. Right, it's not a true quotient rule. We're doing the two separately. So natural log of x, the derivative of a natural log is 1 over the argument. The denominator is 1 over x, or you could think that's like x to the negative 1. So when you do the derivative, you get negative x to the negative 2. Or that's the same as saying like negative 1 over x squared. What would you do here? We clean this up. We have 1 over x times negative x squared over 1. So we can cancel on x, so that's the limit as x approaches 0 from the right of negative x, which will just give me 0. So we had to just use algebra to rewrite it into an equivalent expression so that we could then use L'Hopital's rule. Any questions there? Let's go to our books again. So what we have found is there's another indeterminate form. We have a list. We're building a list of all these different things we can't do the limit of. 0 over 0, infinity over infinity, 0 times infinity, and this one infinity minus infinity. So our strategy, in order to use L'Hopital's rule, we have to be able to write it so that we have 0 over 0 or infinity over infinity. So we're going to try to combine things. So for instance, if I look at this problem. All right, it's gonna make us think for a minute. Secant of pi over 2, so that's like 90 degrees. Cosine is the square root of the bottom over 2, right? So that's, cosine is 0 right there, which means secant is undefined, right? It's an asymptote, so it's approaching infinity right there. Tangent of pi over 2 is also undefined. It's vertical asymptotes, that these are infinity minus infinity. So we can't evaluate that. If I'm going to try to combine these things, so I have a fraction, what could I do? How could I rewrite secant? And tangent would be?
Sine cosine.
Right. So that's 1 minus sine over cosine. So we have a common denominator. So now, sine of pi over 2, sine of 90 is 1, so 1 minus 1 is 0. Cosine of pi over 2 is 0. So now it's 0 over 0, which tells me we can do L'Hopital's. So derivative of 1 is 0 minus derivative of sine is cosine over derivative of cosine is negative sine. If I'm trying to evaluate the cosine of 90 is 0, but the sine of 90 is 1. So 0 over 1, we can evaluate that. It's giving us 0.
Where'd you get the negative cosine, or negative cosine or sine? I don't know.
Oh, L'Hopital, so the derivative of the top.
Negative each?
So derivative of 1 minus sine gives you the negative cosine.
Gotcha.
Any other questions? Okay. I want to jump to example 10. So I'm going to save the indeterminate powers for tomorrow. We're just going to practice these two a little bit more. If I wanted to evaluate this limit, so currently, if I plug in, we have infinity times, okay, this is kind of a mess, isn't it? The natural log of infinity minus 1 over infinity plus 1. So, kind of hard to tell what this is doing here. This is going to be very close to a 0 because it's going to be very close to the natural log of 1. If you have a really big number minus 1 over a really big number plus 1. Probably wouldn't give you one quite as hard to do on your own. But this expression is very close to 1, and the natural log of 1 is 0. So this is an infinity times 0 problem. So we don't know how to do that. What do we have to do instead then? How do we rewrite it?
Could we do conjugate? Do anything?
We really just need to get it so we could use L'Hopital's. So we have two things being multiplied. We have the x, and we have the natural log of this whole thing. We need to move one of them to the bottom. Which one would be easier to move to the bottom? The x. So to move x to the bottom, you just have to make it the reciprocal, 1 over x. Okay, so if I'm trying to evaluate this, the inside, infinity minus 1 over infinity plus 1, that's very close to 1. Natural log of 1 is 0. Bottom, 1 over infinity is going to 0. So now it's 0 over 0, which means L'Hopital's. Okay, now we have to get the derivative of top and bottom. So derivative of a natural log is 1 over the argument. What's going to happen if I do 1 over this whole fraction? could we, well, I'll go ahead and write it like this. So I have 1 over this whole thing. But we have to do chain rule, right? So then derivative of the inside. So we'll have to do quotient rule to get the derivative of the inside. Okay, so low d high minus high d low rho low squared. All right, the bottom 1 over x, that's like x to the -1, so when you do that derivative, you get negative x to the -2. So, very ugly, but we can clean this up. All right. 1 over that fraction, you can think of it as multiplying by the reciprocal, so it would just flip it, make it x plus 1 over x minus 1. This, we get x plus 1 minus x plus 1, x plus 1 squared. And that's negative 1 over x squared. So we're still trying to clean up a little bit. And we could cancel out an x plus 1. And then this, the x's cancel. So I have 2 over x minus 1, x plus 1 times negative x squared over 1. I'll flip and multiply. That gives me negative 2x squared over x squared minus 1. All right, we've done a whole lot of algebra here. Have I lost anybody? We have a couple options. We need to evaluate this limit. If I plug in, I'm getting infinity over infinity, so I can't just evaluate it yet. So we could do L'Hopital's rule again, or we could use the tricks that we've already been using. These were like the ones we were finding horizontal asymptotes of. What trick did I tell you guys you could do? When we did our horizontal asymptotes?
Oh, 1 over the highest power?
1 over the highest power of x, you could take everything times 1 over x squared if you wanted. Or you could do L'Hopital's rule a couple times. So I get negative 2 over 1 minus 1 over x squared. So that's negative 2 over 1 minus 0, or negative 2. What questions do you guys have? Yes, that one was very, very ugly.
Yeah. Give me flashbacks to college algebra.
Good flashbacks.
Oh, yeah.
Right? Okay, let's try another one. See if we can handle some of the ugly. Some problems are definitely worse than others. Some are pretty straightforward. That one, because we had the natural log with the fraction, it just got nasty. Alright, if I am looking at this one, 1 over 0, so 1 over a smaller and smaller number is going to infinity. Sine of 0 is 0, so again we have 1 over a smaller and smaller number, so this is infinity minus infinity. What's our strategy? Look back at number 7. We had infinity minus infinity. What did we do?
Oh,
We had to put them together into a single fraction, right? So we have to have a common denominator to put them together so we can use L'Hopital's. So I have to get a common denominator. That means I have to take this first one times sine x on top and bottom, and the second one times x on top and bottom. So that would give me sine x minus x over x sine x. Does everyone see how I got that common denominator? So now if I evaluate, 0 minus 0 is 0, 0 times 0 is 0. So 0 over 0 tells me L'Hopital's. It's x approaches 0, derivative of sine is cosine, minus derivative of x is 1. In the bottom, we do product rule, derivative of the first, how was it? Times the second plus the first, derivative of the second. Okay. If I plug in right now, cosine of 0 is 1. So we have 1 minus 1, which is 0. On the bottom, sine of 0 is 0. So we have 0 plus 0, which is 0. So what does that tell me? L'Hopital's again. So derivative of cosine, negative sine, minus 1, so derivative of 1 is 0. On the bottom, derivative of sine is cosine. Plus, for this we have to do product rule, so derivative of the first times the second plus the first times derivative of the second. Okay, gotten kind of ugly. Let's see. If I put in a 0, sine of 0 is 0. Cosine of 0 is 1. Plus cosine of 0 is 1. Plus 0. So we have 0 over 2, which is 0. So it got ugly, but we were able to evaluate it at this step. All right. Let's stop here, and I want you guys to try some and see how we're doing. So you should have done the day 1 yesterday, but that means if you had any, if you haven't collected it yet, so if you have any you had trouble with, you can ask. Day 2 is 6 questions. So, not nearly as many as yesterday. You've got a lot of time right now to do those 6 questions.